All right, we have another before and after scenario. So we'll start with the ideal gas law. Now the only constant here is the number of moles, and the universal gas constant is R. Everything else is changing. Temperature is changing, volume is changing because it's asking you what the new volume is, and pressure is changing. So all these variables, we're going to move over to one side, and all the constants, in this case just N and R, we're going to move to the other side. And if we do that, we're just going to divide both sides by T, and we get PV T over T is equal to N and R. And this side is just a constant. So because that's a constant, we can rewrite this as P1 V1 over T1 is equal to P2 V2 over T2, and this is commonly known as the combined gas law. Let's take these values in Celsius and add 273.15 and turn them into Kelvin. That's 298.15. That's room temperature, and that's going to be raised to 125 degrees. So this is going to be T1 and 125 degrees Celsius plus 273.15. We're just going to add 100 to our previous number, so it's going to be 398.15, and that's going to be our second temperature because it was raised. So that's the after. Do a little algebra. I'm going to rearrange this to solve for it's asking us for the new volume, V2. So we're going to solve for that. All right, so V2 is going to equal P1 V1 T2 over T1 P2. Now we can just plug and play. So P1 is, what's the first pressure? There it is, 155. V1, the initial volume, there it is, 1.00. And then T2 is 398 Kelvin, and that goes all over T1, 298. And the second pressure is 605 kilopascals. What's going on here? 601 kilopascals. Gas is, okay. Let's plug these numbers in. All these units are going to cancel out here. Kilopascals and Kelvin. So we're left with liters, 0.342 liters. Or if you want, you can turn that into milliliters.